Alright, so we begin this course on complex function theory, theory of functions of a complex variable. Now first let me give you the prerequisites for this course. The prerequisites for the course is MA 205, the course is MA 205, right. This is a course that is taught here at the IIT Bombay for the sophomore students, the second year students. And so what is it that I expect you to know? I would expect you to know calculus of one and several variables, correct? So what is it that I would like you to know from calculus of several variables? You should be able to tell me what is the Green's theorem, for instance. Everybody here, I suppose, is familiar with the Green's theorem of vector calculus. That is about the level, so that should tell you up to Green's theorem is what I will need, right, from calculus of several variables. So whatever I need from calculus of one and several variables is available in this textbook of G.B. Thomas and Finney, right. Thomas and Finney's book is familiar to everybody, and so this is the material that I will expect you to know. And this course is the CEP course, and so this is about prerequisites, okay. Alright. Now the next thing I would like to tell you is the texts and references. The primary text for this course is Krayzig's book, Advanced Engineering Mathematics, 8th edition, Wiley. I suppose the book has been given to you by, copy has been given, not yet, it is not in the kit, okay, it will come to you either today or tomorrow. And there are supplementary references, and the supplementary references Courant and Fitzjohn's Introduction to Calculus and Analysis, volume 1. It has two volumes, volume 1 and volume 2. The second volume contains material from calculus and several variables, which anyway is the prerequisite. So it's a good idea to have both the volumes together. Of course, you don't have to buy it if you don't want to. This is a supplementary reference, but Krayzig contains everything that I am going to talk about. Courant and Fitzjohn is one of the finest books written, according to me, and I think many of you have purchased a copy of this book last time, and those who wish to buy copies are still available at the campus bookstores, and I would recommend it. I would recommend buying this because this is a very well written book, and it's sort of it's a must for every serious teacher and every serious student who wishes to use mathematics for his work, his or her work, okay. So that's a couple of words about references. Now I want to talk about why should one study theory of functions of a complex variable. What is the significance, what is the use of this theory? Why should one study this subject? You have been teaching this course perhaps, have you been teaching this course ever? You have never taught this course, okay. So maybe your students are going to ask you this question, are you going to be teaching this in the coming semester, right? So your students are going to ask you this question as to why should an engineer learn complex analysis. The subject began roughly at the time of Gauss and Cauchy. Cauchy really wrote his book in 1821, and it's a subject which is almost 200 years old, it's in 2009, and it has developed tremendously in the past 2 centuries, and it's become a very versatile tool for both the pure and applied mathematician. Both in pure and applied mathematics, the theory of functions of a complex variable plays a very central role. How would an engineer use the theory of functions of a complex variable? Why should an engineer know it? Here are a few points which I am putting down in a slide. Here. A few points on the importance of complex analysis. Just let me make a change in this. So here, the first thing that I written here is that it forms a versatile tool in the toolkit of both the pure and applied mathematician as well as engineers. For example, in aerospace engineering, one constructs aerofoils and one uses conformal mapping techniques in the construction of aerofoils. There are certain problems in wave propagation that use techniques of complex analysis. transform methods are very important in the solution of ordinary and partial differential equations. And how do you invert the Laplace transform? In the last course, we saw in great detail the theory of Laplace transforms, but we are not seen any systematic procedure for inverting the Laplace transform. The inversion of the Laplace transform involves complex analysis. So, you can use complex analysis for this purpose. For example, a very classical problem in astrophysics was studied by Wiener and Hopf, and they developed a technique which is popularly known as the Wiener-Hopf technique. This is a technique used for solving certain integral equations, and it has become very popular in engineering. So, this uses heavily techniques from complex analysis. I have just written a few things here that should suffice to give you some indication as to why the engineer should know complex analysis. I can't really go into the details of all these things because that will really be a course beyond this course. I mean, you need to know all the things in this course, and then we can go beyond and look at all these things. So, I will give you some references later on, maybe at the end of the course perhaps, where you will get information about the Wiener-Hopf techniques and the transform analysis, inverting the Laplace transforms and so on. Last time in the previous course, I gave you a book called Schiff, right. If you look at Schiff's book, the third item, this transform analysis, is discussed in great detail. The inversion of the Laplace transform is discussed in great detail using complex variable techniques in Schiff's books. Okay. And construction of aerofoils, etc., there are textbooks available, and there are texts devoted that devote a large section to these problems. We will discuss these texts and references later perhaps if need be, correct. So, this is the use of complex analysis in engineering problems. So, just a few words on that, I can't elaborate on this. All right. Now, we begin with the sequence of lectures in that order. After we have talked about the prerequisites, we have talked about the scope of complex function theory, and now we come to the theme of the first lecture. So, basically what are complex numbers and what are its basic properties. So, under this chapter we are going to be looking at the field of complex numbers. The complex numbers is a form of field, right. It has two operations on them, addition and multiplication, and these two operations are not independent objects, they interact with one another, right. The distributive law relates the addition and multiplicative structure, additive and multiplicative structure. Then we have the notion of an absolute value, we have the notion of an argument of a complex number, and the notion of a principal argument. And then the field of complex numbers differs significantly from the field of real numbers. Why? Because the real numbers is an ordered field. There is a natural ordering on the real numbers. It is not possible to introduce an order in the field of complex numbers. Now, you might ask this following question as to why can't you do this ordering in the field of complex numbers? After all, I can surely introduce an order. Say I take two complex numbers x1 y1 and x2 y2. I will say that if x1 is less than x2, then this complex number is less than that complex number, and if x1 is equal to x2, then look at y1s. It is like what is called a dictionary order, correct. Which word precedes which word in the dictionary? Look at the first letter, right. The first letter is the first word is A, and the first letter in the second word is B, then this one, the word beginning with A comes first. If both the words begin with A, then look at the second letters, right. That is what we have done here. This is an ordering, but this ordering is pretty useless. It is not just enough to have any ordering in the in a set. You want the order relation to interact with the other operations of addition and multiplication. In the field of real numbers, that happens. You can identify a certain subset of the real numbers and call them the positive real numbers. So, if you add two positive real numbers, again you get a positive real number, and you multiply two positive real numbers, again you get a positive real numbers. So, this order relation in the real numbers interacts with the addition and multiplication. This thing that I gave you, this dictionary order, will not have that property. So, it is not just enough to establish an order relation. You want an order relation that is compatible with the algebraic operations of addition and multiplication. Such a thing is not possible in the field of complex numbers. We shall see that. And then the next thing we will look at is the fundamental theorem of algebra, that every polynomial with complex coefficients has a root. We are not going to be in a position to prove this theorem in this chapter. The statement will be made here, and a very special case will be done here, namely the equation z to the power n equal to a. A is a given complex number, and we have to solve the polynomial equation z to the power n equal to a. That will be discussed in detail. So, this is the content of the first lecture, right. This is a list of topics. So, now let us get to them one by one. Any questions so far? No? Okay. So, complex numbers and their basic properties. So, what is a complex number? A complex number is just an ordered pair x, y of real numbers, right. In other words, a complex number can be viewed as a point in the plane. You have plane x axis, y axis, take a point, and that a point in the plane is a complex number. Now, we also use the notation, instead of using the notation x y, we can also use the notation x plus I y, correct. What is this I? We will postpone the discussion of this and get to the properties of addition and multiplication. So, complex number has been defined, it is an ordered pair. Now, I should tell you how to add two complex numbers, and I should tell you how to multiply two complex numbers, right. So, let us get to that. So, addition and multiplication of complex numbers. So, how do I add two complex numbers? x1 y1 plus x2 y2 is what? x1 plus x2 y1 plus y2, component wise addition. Addition is very easy. Multiplication is somewhat strange. x1 y1 multiplied with x2 y2 is x1 x2 minus y1 y2 comma x1 y2 plus y1 x2. This is the rule for multiplying two complex numbers. So, I have introduced in the set of complex numbers a rule of addition and a rule of multiplication. Well, now you want certain properties, it is not just enough to define addition and multiplication, you want this addition and multiplication to obey certain laws. The usual laws of commutativity, addition should be commutative, and that is pretty trivial to see. Right from the definition, you immediately see that addition of complex numbers is commutative. It is equally trivial to see that it will be associative, etc. So, let us go over these basic properties of addition and multiplication. So, I have already spelled out the commutativity of addition. Here I am spelling out the associative property of addition, and then there is a 0 element in the set of complex numbers, right. xy plus 0 0 is again xy. So, 0 serves as a additive identity, and every complex number has an additive inverse. So, these are the four fundamental properties of addition and the complex numbers, addition of complex numbers as defined, they possess these four properties. Okay. Now, let us come to multiplication. This requires a little more checking. Multiplication is commutative, that is easy to see from the definition. Not so obvious is the associative property. You have to check this is an exercise. Multiply this and multiply, work out the left hand side completely, work out the right hand side completely, and check that these two ordered pairs are equal. That will confirm the associative law for multiplication, and it is very easy to see that 1 comma 0 is the multiplicative identity. Unfortunately, not every complex number will have a multiplicative inverse, 0 0 will not have a multiplicative inverse. It is very trivial, because when you take a complex number x comma y and take its product with 0 comma 0, you are going to get 0, 0 comma 0. You are not going to get 1 comma 0. However, if you take a non-zero complex number, that means that remember that the components are real numbers. So, x squared plus y squared is not 0. So, if I take a non-zero complex number, then it will have a multiplicative inverse. What is that multiplicative inverse? I am going to display it for you and it can be verified, correct? Alright. So, that you have taken the xy which was not 0. Since at least one of them is not 0, x squared plus y squared is not 0. So, I can construct this complex number x upon x squared plus y squared comma minus y upon x squared plus y squared and directly check that you are going to get 1 comma 0 when you multiply them. So, every non-zero complex number has a multiplicative inverse. So, now we have the addition. Addition is commutative, addition is associative, there is an additive identity and there is a every complex number has an additive inverse. Multiplication. Multiplication is commutative, multiplication is associative, there is a multiplicative inverse, there is a multiplicative identity and every non-zero complex number has a multiplicative inverse. So far, these two properties do not interact, these two things do not interact. So, if that is all, then there is no need to bring in these two simultaneously. I could study the additive structure separately and I could study the multiplicative structure separately. What makes the thing very interesting is that these two operations of addition and multiplication are intimately related by the distributive law. It is the distributive law that relates addition and multiplication. So, the distributive law is very important. So, what is the distributive law? Multiplication distributes over addition. It is absolutely easy to check this. That is, it is both left and right distributive because of the commutative law, correct. So, multiplication distributes over addition both from the left and from the right. So, now we have these 9 properties, 4 for addition, commutativity, associativity, additive identity, additive inverse, 4 for multiplication, commutativity, associativity, multiplicative identity and existence of multiplicative inverse for non-zero complex numbers and the distributive law which relates the two. So, any system having all these properties is called a field. Real number system also has this property, right. Real numbers also have these two operations, addition and multiplication, and all these 9 properties are valid for real numbers also. So, real numbers form a field, likewise the complex numbers also form a field. Take the set of all n cross n matrices, how many operations are there? Again I can add 2 n by n matrices and I can multiply 2 n by n matrices, right. Does it form a field? No, because not every non-zero matrix will have an inverse, correct. Secondly, the matrix multiplication is not commutative. So, it is a ring, it is what is called as a ring, it is not a field. 0 divisors are there, yeah, that is a problem. But here there are no 0, every non-zero complex number has a multiplicative inverse. So, it is a set of complex numbers form a field. So, the set of complex numbers C with the addition and multiplication obey the same laws as the real numbers do, namely they form a field, correct. Now, let us calculate 0 1 dot with 0 1. The result is minus 1 comma 0. Now, if you look at these complex numbers of the form x comma 0, how do they behave? So, let us look at these complex numbers x comma 0, right. Let us see their, let us understand their behavior. If I take x1 comma 0 and x2 comma 0, it is simply x1 plus x2 comma 0. x1 comma 0 multiplied with x2 comma 0 is simply x1 x2 comma 0. The additive identity and the multiplicative identity are both of this form x comma 0. So, these things, for all practical purposes, I could forget about the 0 and I can simply identify the x comma 0 with the x itself, correct. So, the real numbers can be thought of as a subfield of the complex numbers, right. So, every real number x can be thought of the complex, can be viewed as a complex number x comma 0, right, and the 0 and the additive identity is a real number and the multiplicative identity is also a real number, remember. So, it is a subfield. Well, if that is the case, then let us go back to the previous equation. How does this equation translate to? This equation simply translates to saying that the square of this complex number 0 1 is a real number minus 1. So, minus 1 has a square root in the set of complex numbers, and this special thing 0 comma 1 is denoted by I. So, now we have a new phenomenon occurring here, that minus 1 has a square root, namely 0 comma 1. It has two square roots, 0 comma minus 1 also, but let us take 0 comma 1 and call it I and call the other one minus I, correct. Well, in that case, if that is the case, then I can now write down this complex number x y as x comma 0 plus 0 comma y. X comma 0 can be written as x comma 0 into 1 comma 0, 0 comma y can be written as y comma 0 into 0 comma 1, but we have agreed to call 0 comma 1 as I, and we have agreed to think of y comma 0 as simply the real number y, and so the left hand side is x comma 0 is simply the real number x, and 1 comma 0 we have agreed to call it 1, correct. So, under our, with this usual identification of x comma 0 with the real number x, we see that the complex number x y can be more conveniently written as x plus I y, where I is the square root of minus 1. In the set of complex numbers, minus 1 has a square root. Real numbers don't, this is not the case in the real numbers. In the set of real, in the field of real numbers, minus 1 is not a square, whereas it is whereas minus 1 is a square in the field of complex numbers. So, that particular one of the square roots has been called I. The square root 0 comma 1 has been called I, and our complex number x y is simply x plus I y. Is it clear? So, now we have explained what the I really meant, and in the process we have also done the whole job of putting a field structure. We have made the set of complex numbers into a field. We have introduced two binary operations, correct. All right. So, now under this notation, the rules can now be easily written as x1 plus iy1 plus x2 plus iy2 is x1 plus x2 plus I into y1 plus y2, and the rule for multiplication is written in this form: x1 plus iy1 dot x2 plus iy2 is x1 x2 minus y1 y2 plus I into x1 y2 plus x2 y1. The rule for multiplication assumes this form, and the complex number 0 comma 1 has been called I, and I squared is minus 1. And then associative law, commutative law, everything works. So, when you have two complicated expressions, you can simply use the rules of associativity, commutativity and distributivity and simplify those into little pieces and use this additional information that I squared equal to minus 1. That is all. So, the algebra, doing the algebra with complex numbers is pretty simple. It is just like, it is exactly the way you will work out expressions. In high school algebra, you will, how do you simplify this x1 plus iy1 and x2 plus iy2? You will use distributivity, right? x1, x2 plus I squared y1, y2. I squared is minus 1. So, that is how you get the first piece. And so it goes. So, the rules of algebra simply go through without any problem, except for one additional feature that I squared is minus 1, right. So, in the complex number x plus iy, x is called the real part and y is called the imaginary part. The imaginary part is y, not iy, remember that convention. All right. So, typically complex numbers will be denoted by letters z or w. Occasionally, we will use the letter zeta to denote a complex number. The Greek version of the Greek analog of z will be zeta. The real part of z is denoted by re of z. Imaginary part of z is denoted by mz. And the modulus of the complex number, suppose if I take z equal to x plus iy, where x and y are real, what is the modulus of the complex number z? It is square root of x squared plus y squared. So, a complex number is viewed as a point in the plane, correct? And so, what is the modulus? It is simply the distance of the complex number from the origin. Distance of the point from the origin is the modulus of the complex number. And then what is the notation for the absolute value? Simply mod z, right. Here are some very simple exercises which you should work out. I mean, really the second one is the second and the third one are the most important ones. First one is simply a matter of multiplication, but the first one is quite interesting. It is really it is a very interesting identity. It's the first one is an identity in sums of squares. So, even if you write down the left hand side and write down the right hand side, it would be an interesting thing to see what comes out. When left hand side, when you expand, what is it going to be? x1 x2 minus y1 y2 the whole squared plus x1 y2 plus y1 x2 the whole squared. So, the sum of two squares factorizes in the right hand side, square both sides, because you get rid of the square root. So, left hand side will be what? Square of the left hand side will be x1 x2 minus y1 y2 the whole squared plus x1 y2 plus y1 x2 the whole squared. It's a sum of two squares. Right hand side is a product of sums of two squares, that x1 squared plus x2 squared into y1 squared plus y2 squared. So, very interesting identity, it's a very important identity, that when you take sums of two, when you take a sum of two squares and multiply two such, the result is again a sum of two squares. Second one is called the triangle inequality. Third one is a corollary of the triangle inequality, which is often useful. The second exercise is a little involved. Show that every non-zero complex number has two distinct square roots. I mean, I want you to take the complex number a plus ib and I want you to tell me two complex numbers which when squared will give me a plus ib. And these square roots have to be described using a, b and radicals, correct? Can you do it? Can you try it? So, assume that x plus iy the whole squared is a plus ib. you get pair of simultaneous equations for x and y, solve them and find them out. Okay? Is it clear? Shall we move on to the next slide? Now let us come to the argument and the principal argument. The next topic is, subtopic is argument and the principal argument. So take a non-zero complex number z. So divide the complex number by the length, by the modulus of the complex number. What is it going to be? It's going to be a unit complex number, right? It's like what you do in vectors. You take a vector and divide by the vector by the length of the vector, you get a unit vector. So that's a unit vector. A plus, call it A plus IB. Then what do you know about these two pieces A and B? They are both between -1 and 1, right? When you take a unit complex number z upon mod z, A and B are both in the interval -1 to 1. Is it clear? I mean, I am sorry if some of these things will be familiar to you, but for completeness this has to be done. However easy it may be, however boring it may be, I apologize to those people who find it very boring, because we can't get on without setting down, laying down notations and conventions, right. So let us get through with this. So you take the complex number z and divide by the length, call it A plus IB, and this real part and imaginary part are both between -1 and 1. Now the cosine function takes all values between -1 and 1, right, the intermediate value theorem. So if A lies in between -1 and 1, then A must be cos theta. I am going to assume the theory of trigonometric functions from the of real variables. So there exists a unique theta in the interval 0 to pi such that A equal to cos theta, correct. When you restrict the cosine function is a periodic function, it is an even function, it is an even function. So first of all, it is a periodic function of period 2 pi. So if I just have to restrict it to the interval -pi to pi, but it is an even function. So I just have to restrict it to the interval 0 to pi. But then once I restrict it to the interval 0 to pi, it will become 1 to 1, correct. So there is a unique angle theta in the interval 0 to pi such that A equal to cos theta, right. In that case, B is what? Remember, A squared plus B squared is what? 1, because Z upon mod Z is a unit complex number. So B is going to be plus or minus root of 1 minus A squared, which is, that means B is going to be plus or minus sin theta. So now let us take two cases, or rather three cases, B bigger than 0. If B is bigger than 0, which sign should we take? We should take the plus sign, because theta runs from 0 to pi. There sin theta is positive. So then I have to take the plus sign, and I have A equal to cos theta, B equal to sin theta, and Z upon mod Z is cos theta plus I times sin theta, or Z equal to mod Z into cos theta plus I times sin theta, and this theta cannot be 0 or pi, because I am assuming that B is positive. This takes care of the case when B is positive. Now let us get to the case when B is negative. When B is negative, again theta cannot be 0 or pi, because B is negative, B is not 0. So A is what? A is again cos theta, but B has to be minus sin theta, because B is negative, whereas sin theta is positive. B is plus or minus sin theta, and we have to decide which is the correct one. So now we have fixed the sign. So now A can be written as cos of minus theta and B is nothing but sine of minus theta, and where is minus theta? In the interval minus pi to 0. So again Z equal to mod Z into cos of minus theta plus I times sine of minus theta. So let us call it Z equal to mod Z into cos phi plus I times sin phi. Let us call minus theta as phi. But this time phi is in which interval? Minus pi to pi, correct? So every time it is, third case is what? We had looked at the case B positive, B negative, now B is 0. If B is 0, then A cannot be 0. Remember, we are taking a non-zero complex number. So A cannot be 0, but A squared plus B squared is 1. So A is either going to be plus 1 or minus 1. If A is 1, then theta is 0. If A is minus 1, theta is pi, because theta is in the interval 0 to pi to begin with. So again Z will be mod Z into cos theta plus I times sin theta. So in every case, we are able to find an angle, we are able to find a unique angle in the interval minus pi to pi, open at minus pi and closed at pi. The case pi occurs when B is 0 and A is 1. I am removing minus pi to pi. Okay, or let us keep the uniqueness aside. In every case, we assert that there exists an angle in this range minus pi to pi, minus pi excluded, pi included, such that Z equal to mod Z cos theta naught plus I times sin theta naught. So there exists such an angle. Now it's an exercise for you, okay, to show that this angle is unique. First of all, I took a complex number Z. Z upon mod Z is a unit complex number, A plus IB. A was cos theta, and accordingly we fixed up B as either sin theta or minus sin theta. If it is minus sin theta, then change theta to minus theta. And in every case, we are able to find an angle in the range minus pi to pi, minus pi excluded, pi included, such that Z equal to mod Z into cos theta naught plus I times sin theta naught. Is this clear? Now we get to the uniqueness. Now suppose there are two such angles, theta prime and theta double prime, such that Z upon mod Z is cos theta prime plus I times sin theta prime. It is also equal to cos theta double prime plus I times sin theta double prime. Then what happens? Cos theta prime equal to cos theta double prime, sin theta prime equal to sin theta double prime. So theta prime minus theta double prime must be 2 pi k, where k is an integer. That's an exercise for you. Both these conditions are required, by the way. You can't arrive at this conclusion with only one of them. Both are required. You need both equations, cos theta prime equal to cos theta double prime and sin theta prime equal to sin theta double prime. Then you are able to conclude that theta prime minus theta double prime is 2 pi k, where k is an integer. So what is its modulus? Absolute value of theta prime minus theta double prime is 2 pi mod k. But where is this theta prime and theta double prime coming from? Look at the very first line. They are both in the interval minus pi to pi, minus pi excluded. So what is the difference? The difference will be strictly less than 2 pi. On the one hand, the difference is 2 pi times mod k. On the other hand, the difference is strictly less than 2 pi. So what is the only choice? K should be 0. If k is 0, that means that theta prime equal to theta double prime. We have given a very careful argument here that there is a unique angle theta naught in the range minus pi to pi, minus pi excluded, pi included, such that z equal to mod z cos theta naught plus I times sin theta naught. Is this point clear? So, given any non-zero complex number, there is a unique angle theta naught in the range minus pi to pi, minus pi excluded, pi included, such that z equal to mod z cos theta naught plus I times sin theta naught. Yes? This unique angle theta naught is called the principal argument. This unique angle theta naught is called the principal argument of the complex number z. Is this clear? And is denoted by capital arg z with an uppercase A. Remember, any theta with the property that z equal to mod z cos theta plus I times sin theta is called an argument of z denoted by little arg of z. So, now we have two concepts, the principal argument and general argument. What is the relationship between the principal argument and general argument? Remember that if theta prime and theta double prime are two such angles, then the difference is 2 pi k. So, any two arguments will differ by 2 pi k, where k is an integer, correct? But the principle, but that particular angle which lies in the interval minus pi to pi, minus pi excluded, pi included, is called the principal argument, and we are going to use the capital ARG for denoting that, correct. So, now that defines a function for you, z going to capital ARG z, call this, that is a single valued function, that is a well defined function. For each z there is a unique angle, remember, that is an argument function, right. So, that defines a very important function in complex analysis, the argument function. In contrast, the other function here, z going to little arg z, is an example of what is called as a multivalued function. Remember, in mathematics, you do not allow functions to be multivalued, right. Functions are by definition single valued, but unfortunately in the study of complex analysis that is too restrictive. If you insist that functions should be single valued, then the price you have to pay is somewhat heavy, because this angle function is really not a single valued function, it is a multivalued function. So, you have two choices, either you have to allow functions to be multivalued at elementary level, that is really fruitful, or you continue to insist that function should be single valued, but then look at the last part, you have to work with a complicated object called the Riemann surface. The contrary to, so let us see what is written here. Contrary to standard conventions, we must allow in complex functions, we must allow in complex function theory multivalued functions. The little argument, the little arg, is a naturally occurring multivalued function. To restore its single valued nature, to avoid this unpleasantness, you need to resort to heavy technology, the theory of Riemann surfaces. You need to develop the theory of Riemann surfaces in order to restore the single valuedness. Clearly, that is outside the scope of this course, and I think it is slightly easier and perhaps It's much more intuitive to allow the argument to be multivalued. Now you see this problem appears in physics also. In classical mechanics, you see this angular velocity function is always a problematic thing. Remember? What is angular velocity? Suppose you study circular motions, etc. What is angular velocity? d theta by dt. But what is theta? The particle is performing circular motion. After it has performed one circuit, the angle has changed, it does not return to 0 angle, because if it were to return to 0 angle, then that means it will become discontinuous. No, the particle starts from the top, and the angle continually increases, and as time passes, it becomes closer and closer to 2 pi, and now you say that when it returns to the top, from 2 pi it has jumped to 0 again. Well, if the angle function is going to be discontinuous, how can you differentiate it? Then d theta by dt will not make any sense, isn't it? So you see there is a problem in defining angular velocity. What you do is that the angle function should be viewed as continuously varying. When the particle completes the circuit, when it returns to the original position, it is not 0 now, it is 2 pi. When it makes 2 circuits, it is 4 pi, and so on. And so you have to allow the angle function to be multivalued now. The particle has reached the same point. It is a single valued function as time, but as a function of space, it is multivalued. That is the problem. If you don't do this, then you are going to run into difficulties. The same difficulty will appear in complex analysis. Well, the question is that, are you looking at the function as a function of time, or are you looking at the function as a function of the point? Right. Yes. Yeah. So multivalued functions appear naturally in complex analysis. You can't avoid it. We shall see more illustrations of this as we go along. The square root function, for example, in real analysis, we will say root x will denote the positive square root of x. But the problem in complex analysis is that there is no such thing as positive or negative. Remember, I mentioned some time ago that there is no ordering in the field of complex numbers. There is no way to choose one square root over the other square root. It is not very clear which one to choose. There is no distinction, there is no way to distinguish in any natural way. So both the square roots have the same status. So the root z, the square root function, is a multivalued function. You have to allow it. You have to allow the multivaluedness. It's a two-valued function. There is no way out of it, really. The only way out of it is to introduce the concept of Riemann surface. Really, there is really no other. There is no shortcut. All right. Yeah, we will continue this lecture. We started late, so I will continue this in the afternoon because I would like to finish this elementary part, and so we will continue this in the afternoon at 2 o'clock. Thank you.